All right, let's get started with this evening's talk. Tonight we have Mark Beach from Beach Dynamics. Back in '84 you started. About then, and a master's degree in mechanical engineering from the University of Cincinnati. Mark travels around the world, works with all the big companies and solves their problems, works with the, audio, loudspeaker and... Alti. That's easier.
Audio and loudspeaker technology.
Yeah.
International.
So, Mark and I talked about it. Mark is really a subject matter expert on this topic. So when he asked me where to start, I said, well, why don't we start with sort of the basic understanding, and we'll work our way up. So feel free to challenge him, and hopefully maybe we'll have him back to hone in a little bit higher for us. So I'll turn it over to Mark now.
Go figure. Yeah, we'll be okay. Hopefully everyone can hear me. Is this on? So what we're going to do is I'm going to move along quite rapidly, but we're going to cover very broad topics from sound, room acoustics, loudspeakers, and then we're going to talk about no free lunches because apparently there was some confusion in the advertising. So basically electroacoustics is a combination of doubly electrical engineering, MEs, and acoustics or physics. And in the US, there's really no one that has a program for that. In Europe, they do have electroacoustics programs, and they are the leaders, especially in Northern Europe. But loudspeaker design is basically an exercise in compromises. And the recurring theme tonight is you're going to see no free lunches, because every time I say, okay, we can do this, I'm like, well, we got to give up that. And as you guys are in the engineering field, or many of you are, you know that it's all an exercise of compromises. So first I'm going to start out, I'm not going to get into vessel functions and real and imaginary impedance, acoustic impedance, and things of that nature. But I want to cite an example, which is a fast Fourier transform, and how the industry has kind of lost its direction. The Fourier transform basically took time domain information and put it in frequency domain. And this was a quantum leap forward for the loudspeaker industry, and it was great because we put an algebraic version, which is called the fast Fourier transform. Once we had a computer, we could start doing this. And it was a quantum leap forward. However, engineers started relying on metrics too much. And so when you go into your boss, you just can't say, hey, I designed this loudspeaker, and it sounds better. That's strictly subjective. So you start relying on more and more on metrics, including the Fourier transform. And what happens is we've lost sight, because this is what we really are trying to do. We're trying to be magicians, and we're trying to be illusion, but it's audio illusion. And so I kind of have this as a Edison, and this is a famous singer, Frida, and she's fooled all these guys with this, this Edison, which is kind of laughable, but nevertheless, that's what we're trying to do. So when you think of sound, I want you guys to think about ping pong balls. I want that to come to your mind. Because instead of a mathematical, I want you an intuitive feel for what's actually happening. And that is molecules are kind of bouncing around. And so this is kind of what it looks like, so to speak. But I want you to, what do we do when we have ping pong balls in a control volume? Well, if you have ping pong balls, you have a ping pong paddle, and you whack them. And in our industry, whacking the ping pong balls, we have anywhere from a 1/2-inch driver up to 21, which is there, and we even have 24-inch drivers now. And so what happens is when you hit them, you obviously compress them, but instead of bringing your ping ping pong paddle back to neutral, you actually go negative with it, pass to rest. And you get zones of pressure and rarefication. And if you do this repeatedly, you have a frequency, and it goes flying across the room. And it goes flying across the room about 1,130 feet a second. So a nice, easy way to remember is 1 foot per millisecond. And this will come back to us a little bit later. But the question is, when it goes across the room, well, what happens when it hits the wall? And as it travels across, it comprises of pressure energy. Let's say you have 1 acoustic watt. It's comprised of pressure energy and velocity energy. And as it goes across the room, it goes back and forth between pressure and velocity. It's velocity here, it's velocity here, and high pressure there, but still 1 acoustic watt. Well, when it hits a wall, well, what happens? Well, what's the velocity at the wall? 0. So it's 100% pressure when it's on the wall. Now, theoretically, that sound wave will come off, and once it's millimeter from the wall, it's back to 1,130 feet per second. But in reality, with sound bouncing all over the place and waves coming from different directions, what you get is a pressure buildup at the wall. And so it becomes kind of a traffic jam of ping pong balls. And then where a wall meets the floor, wall meets the ceiling, or 2 walls meet together, the traffic jam gets even worse, and it becomes all pressure. And down in the corner where 3 surfaces meet, the pressure is real high, and that's where you're going to see the highest pressure. This will come back to us in a minute. So I want to talk about room acoustics a little bit, and I want to stress that the room is a vital part of the playback system and is neglected by everyone. There are audiophiles out there that are spending thousands of dollars for a power cable, an interconnect cable, all kinds of things, and completely neglect the room. The room is a vital part of the playback system. This is a place where they play music. It's down in Cincinnati. Very bad acoustics. I had to design, absorbers and things that when kids hit them with the ball between classes, they don't get destroyed. But I turned this into a venue that was basically unusable to one that they could use for weddings and receptions, etc. So the one metric we have with rooms is called reverberation time, or RT60, and this is basically the time it takes to sound energy to decay 60 dB. In reality, that's very hard to measure. Normally we do RT30 and then extrapolate. In this particular one, I want you to point out that what we do is we energize the room. You can do an impulse, but in this particular case, this is a recording studio that I designed in Boston. And in this one, what we did was, instead of like an impulse noise, we fill the room up with noise until the rated, the energy going in equals the energy coming out, and it kind of reaches steady state. And then all of a sudden we kill the noise and we measure how much time it drops down. In this particular one, the RT60 was a half a second. And normally when you're in a room that's not treated well, you'll get little blips going on right here, and it's kind of like slap echo. So if I go bang, I'll wait a little bit, and all of a sudden I hear another bang coming back. That would be like a slap echo. But the way this room was designed, we don't get that. The other thing I want to point out is this is absolutely phenomenal, because this is basically steady state. We want the reverberation time to be the same for all signals, no matter what the frequency. Now, if you notice, it starts rising, so I'm good down about 250, it starts rising. But even at 63 hertz, reverberation time is really good. And this is, you don't want too much, you don't want too little reverberation time, because then you're in an anechoic chamber and the sound doesn't sound very good, it just sounds real dry. So how do we treat a room? Well, basically you got absorbers and you got diffusion. So right here we have this is an anechoic chamber I built in for Whirlpool in Iowa. And so these are what's called Varanic wedges, but these are velocity absorbers. They're like filled with fiberglass. Over here we have acoustic foams and fiberglass, rock wool. These are all velocity absorbers, and their function is basically the function of the thickness. So you can go, 2 to 4, you can do a lot better. 4 to 8, you can do a lot better. But if you want to absorb 20 hertz, which is the bottom of our hearing, then this wedge right here is 13.5 feet long, which means you go 13.5 feet this way, 13 this way, 13 this way, 13 this way. And you can see I want all of you guys to go home and put these in your living room when you get home first thing. A quick note here that if any of you guys do anything in acoustics, there's a lot of really cheap foam that works great. It's polyurethane, and other urethanes, and the problem is that it's a petroleum product and it burns. And so, sorry about this. So when it burns, if you remember like the White Fang concert in Boston that killed a whole bunch of people, I think it was White Fang or White Shark or whatever. That was because they had acoustic foam that was a polyurethane, and the fireworks set it off and it killed like 80 people. So you can get a lot of this from China and it's really cheap, but the melamines are what you want. Now the other type, so this is a velocity absorbers. The other type is what's called a pressure absorber. So it absorbs pressure, and these are Helmholtz resonators. And they usually have like a Q. They have a Q here, but these guys have done such a good job that the Q's absorption, they've made it a wideband absorber. If you notice, this is, it's just not a discrete frequency. It goes pretty wide. But they put this in a corner. Why? That's where all the pressure is. And so you have pressure absorbers and velocity absorbers, but if you put the velocity absorber on the wall, it's not quite as effective. But unfortunately, that's really about the only place we can put it. You can't put it out in the middle of the room. But anyways, I wanted you to understand that there's two types of absorbers and there's different places for them. So in this studio we built, we put diffusers that had a special characteristic, and they had absorption. These are the diffusers. They're polystyrene, and they had kind of an absorption, but minimal absorption, because the diffuser, you don't want it to absorb any energy. The sound comes in, hits it, and it bounces. Here's what you're trying to do. You're trying to get a discrete slap echo to hit, and then it takes that one acoustic watt goes in, one acoustic watt goes out, but instead of discrete angle, it's coming off at all angles, and so it's not objectionable. And normally they have zero absorption, but we designed these where they have some absorption, and these were made cost feasible. These are very expensive to make, except somebody in this room utilized an advanced technology to make these cost affordable, and this is Bill Bankus, who's one of your guests here. So Bill was instrumental in how these are made, and by the way, these are all removable so that we can vary the room acoustics. So if you have a choir coming in, you take a bunch out so we get that reverberant, but then if you have a rock and roll group or whatever, you want low reverberation time.
So you said that was polystyrene. Is that like styrofoam?
Yes. A fire retardant polystyrene. And so these are phenomenal. They're so good that we're trying to figure out how to take them to market right now, because normally, a 2x2 like this, it's probably $400, and we can under normal technology, but we're trying to beat that. So finally we get to listening to a couple speakers in a room, which is the ultimate goal. And I'm kind of covering all this lightly, and then whatever interest we have at the end, we can go in more detail. But right now, I'm just kind of skimming across the best I can. So what the point I'm trying to make is, if you have two-channel stereo, you're going to see something here, you got what's called the sweet spot, and that's kind of like everyone knows it. But the sweet spot, it'll have a couple speakers that are off the back wall, off the side wall, and it's symmetry. Everything here is symmetry, distance from right to left. And what happens is the brain doesn't recognize this reflection if it's short enough. And you'll come back and it'll be a wide image. About 80%, maybe 90% of the market likes a wide image. And that, what I mean by that is if it's done correctly, you're sitting down, you close your eyes, you can't point to the speakers. You can't point to them. You just hear it and you're like, well, the singer's here, the guitarist is here, and that's what we're trying to achieve because remember, we're trying to be musicians. This is kind of what we're trying to achieve. If you look over here, this right here is the direct sound, and this is the reflected sound. And one of the things we're trying to do is we're trying to get the reflected sound that have the same shape. It may be down in magnitude, but we want it to have the same shape, so to speak, of the direct sound. Because if it has a different shape, then our brain, we don't go, oh, well, the reflected sound is bad. Our brain isn't that good. I mean, our brain is amazingly on sound. But you'll go, well, I just don't like that. There's something wrong. I don't like it. It's not quite good. And that's your brain picking up that the off axis, off the walls is not good. So one of the things we'll get into a little bit later is, well, your speaker better be playing, in this case, 45 degrees, better be playing the same signal this way as it does this way. And that's the hard one. That's hard. That's really hard to do. The third one down here is just kind of a same signal, but it's very low and kind of random. And that kind of gives you a sense of euphoria. If you don't have that, it just sounds like you're in a dead room. And an anechoic chamber is a horrible place to listen to loudspeakers. So finally, we're getting into the type of ping pong paddles. And so what we have, most of the ones on the table, I do have a ribbon over here, and I do have a compression driver, but most are voice coil dome and voice coil cones and domes. And basically, it's just a linear actuator motor. And we'll go into more detail in a little bit. The other one is a horn loaded. It's really the same except as a voice coil driven. It's got a voice coil right here, except it's got a diaphragm right here. And when most people say, well, it's a horn, generically, they mean this thing, and on the front of it is this device, which is the horn. In the professional world, this is a compression driver, and this is a horn. This is a passive device, and all it is it's the same as an electrical transformer, except it's impedance matching device for acoustics. The reason this is called a compression driver is because this diaphragm that goes right along this blue, it moves forward, and you can tell it compresses all the sound in, and then it slowly starts expanding until it hits the horn and expands. So it's actually compressing the signal, and the benefit is you get a lot higher efficiency. As a matter of fact, this one right here, you probably get about 25% efficiency. But remember the recurring theme, no free lunch, right? You compress this much signal, the byproduct is, there's two byproducts. One is distortion and the other one is directionality. That horn has a certain direction that it plays, and outside of it, it's horrible.
I assume the cost goes from left to right and up.
The what now?
The cost. If you use the lower left thing, that's the cheapest thing up there, right?
These are probably the more expensive ones. This is real expensive, that's the cheapest. So,
Going the wrong direction.
yeah, well, they all have different purposes and different applications. So this is about 25% efficient. This is about, if you get a highly efficient version, it's 1% efficient. That's high efficiency. So your amplifier sends 100 watts to it in electrical power, you get 1 acoustic watt out of it. This one here, this is an electrostat, which is basically a big capacitor. Your amplifier looks downstream and it doesn't see a resistor, it sees a capacitor. It's a big plastic film, and it's put in a field between two perforated plates. Vibrates back and forth. They usually have to be big because they can't vibrate very far. These are exceptionally good sounding, but they have their drawbacks. No free lunch. They don't have bass. They don't have treble. They can, and there's ways around that. This is probably about 0.1% efficient. That means 100 watts into it, you get 0.1 watts out of it. This one over here is a planar magnetic. I've got an example up here. This is kind of the same thing, except the voice coil, this voice coil right here is on the membrane itself, and it winds up and down. Yes, sir.
Where's all that energy go? Is it all heat?
Heat.
And why don't the speakers get just hot, hot, hot? I don't remember.
They do.
I don't remember seeing fans on speakers like to keep them
They,
cool.
no, they get hot.
But they just get hot. They
Right,
radiate.
so what happens is, and I'll jump aside on this. See this right here? This is solid. In most of them, there's a tube that goes up there, and the tube, the entrance and the exit of the tube are dissimilar. And that's so it pumps air. When the speaker starts going like this, it starts pumping air, but it sees a different resistance. If it had the same resistance on both ends, the volume of air would just sit there and go like this. Well, if you have different resistance, if you have a different resistance up here on the top versus this one at the bottom, and we'll probably show later on, then the air kind of goes like this, and it takes the heat out. But yeah, that's a problem. And so, by the way, a loudspeaker, I can blow a loudspeaker up with 1 watt if I do it at high frequency. Because at high frequency, the cone's not moving. It's just sitting there going like this. At low frequency, it's going like this. Well, what's it doing? It's pumping air across the voice coil, it's cooling it off. But I can take a high-powered loudspeaker, put 1 watt into it. By the way,
So Mark, a question, why wouldn't you cool it then? Why wouldn't you put a cooling system in it?
I think it's money. I've thought about it. I've thought about putting a fan on it.
But you don't even need a fan, you could actually do something different.
I think they engineer their way around it, and it's cost.
Okay.
I agree 100%. I've thought about fans. I've thought about all kinds of things. But, you know, I'm trying to put, you know, food on the table Monday through Friday, so to speak. And these are pipe dreams that I'd love to look into, including I've got other pipe dreams I'll show you about. But
Don't some have fins?
oh yeah, they'll have fins. You know,
So that
this-
anticipates some of it.
yeah. Here's a tweeter. I don't know if you guys can see it there, but here's a tweeter, and it's got fins on it. And by the way, it's a dome, but so it's a voice coil driver, but it has a small what they call a waveguide, because they don't like calling it a horn. Horns are bad. They call it a waveguide, so it's got a waveguide on it. Anyways, so this is 1 watt. You'll get 90 to 87 dB, somewhere lower, by the way. Here you get 1 watt, you get about 106. 1 watt on this, you get about 82 dB. And when I say those dimensions, those are at 1 meter. If anyone gives you a pressure, this is just a general, no matter if you're doing noise or whatever. If someone says, well, I have a sound pressure level of X, that is meaningless to me. It doesn't mean a thing, because it has to be attached to a position. In this particular case, it's 1 meter from the loudspeaker, is what our ratings are. Out there, it's 1 meter from the property line or whatever. So what I'm saying is pressure has to be assigned a position. So we got the loudspeakers, we got a bass speaker, we got to do something with it. Well, the first thing we can do is we can just slap it on a flat board. And this is the simplest, and there's some advantages, but the problem with this is when the speaker goes forward, it creates a positive pressure, right? And it goes across the room. That's all well and good. Well, when the speaker goes forward, what happens to the pressure behind it? It goes negative. So the negative pressure goes around to meet the positive pressure goes around to meet the negative, to equalize, and they cancel. So this is called an open baffle, and it has its limitations. I'm going to come back to it right away. But that, and the base cutoff, the frequency, how low it can go in frequency is a function of this distance from back to front. And in the opening page, I had one where if you're smart, you can do tricky things by folding this and making that dimension longer. So you say, well, okay, that sucks. What do we do now if a flat board doesn't work? And the answer is, well, let's just stick it in a box. We'll physically separate the positive front pressure from the negative rear pressure. Well, that works great, but then, and this is called a second order system, and it works pretty good. In order for this driver to work in that box, it has to have kind of like poor qualities. So there goes our free lunch again. But because it's a second order system, its impulse response is actually pretty good. The impulse response on this is phenomenal. I mean, it is phenomenal. So we put it sealed, and you're like, okay, you know, it's extended our bass, but I want more bass. Well, we can do a vented bass reflex, which is a Helmholtz resonator, and the parameters of this woofer are matched to the volume of the air, matched to the length of this tube and diameter. And that'll extend your bass even further, and we'll do, at the end, we'll do a model. That'll extend your bass even further. But once again, what's tonight's theme? No free lunch. This is a fourth order. Its impulse response is worse. So best, second best, third best. Sometimes you can get an alignment where this tube is physically bigger than the box. Well, what are you going to do? Well, you do what's called a passive radiator, and what it is it's a speaker cone with no motor on it. But mathematically, a passive radiator and a bass reflex or vented or ported loudspeaker, whatever you want to call it, these two are mathematically the exact same. They're both fourth order. I've done passive, I've done bass reflex. You know, they have their advantages, but they're not quite as fast because they're fourth order. There's a sixth order. I'm not going to get into it because, in my opinion, it's junk, but we'll leave that go. The next one I want to talk about is the transmission line. So if you look, the back wave comes off, and it kind of goes down this long, tortuous path, so to speak. And this is filled with material that slows the speed of sound from 1,130 feet per second in air. It slows it down to 1/4 of that. And then this is a quarter wavelength long at some desired frequency. So by the time this back wave comes around and comes back out the front, it's back in phase with the front because you've slowed it down one cycle. Last but not least is a rear-loaded horn. I've done these. They're quite complicated, but they work great. And if you notice, just like a horn that has a flare, just like the horn that has this flare, right? It's an impedance matching device. You'll see that here, if you look at it, this is actually getting bigger and bigger and bigger. That's a horn. But the guy, instead of just making a big long horn, he's folded it in such a way that it's made it compact. And these have some advantages. They're very efficient. So there's a couple types of speakers. You can have a full range, which has some unbelievable advantages. The full range has the highest impulse response. It's fast. It's phase coherent. Everything works good. But the problem is no free lunch. And so with the full range, you normally lose a little bit of low frequency, a little bit of high frequency. And so what happens is you're like, well, you know, I need those others. You're like, okay, well, let's go to a multi-driver. Well, over here we have a three-way. And we use, this is parallel filter networks. There's series networks, which are really good, but they're hard to calculate, and I don't want to get into it right now. But these are parallel networks, and so we have an inductor on a woofer, and that cuts the high frequencies. And here we have an inductor and a coil, an inductor and a capacitor, and that's a band pass, cuts off the lows, cuts off the high. And up here you have a capacitor which cuts off the bass from getting to the tweeter and destroying the tweeter. And you're like, oh, that works great. Well, not quite, because what happens is they have real slow slope. This is a 4th order, and the slope here is 6 dB per octave. So what you end up with is you end up with the mid-range and the tweeter are actually both playing the same signal, and they do it for, like, in this particular case, 2 or maybe even more octaves. That's bad news. You don't want 2 speakers trying to play the same thing to the audience. It's screwing up the image, the illusion. And the other thing that happens is every time you put one of these elements in there, there's a phase shift. So instead of the speakers going like this, they're going, and the phase shift is so much that if we go to, you say, okay, well, Mark, I don't want these overlapping speakers playing. I'm like, okay, well, let's go to a 2nd order slope. It'll help a little bit. So here we go. We got 2 elements there, 4 there, 2 there. We went from 4 elements to 8. And this is so out of phase that it's 180 degrees out of phase. They actually reverse the polarity on the mid-range. Because it's 180 degrees out of phase, well, then we'll just run the motor backwards. And that's why you see that. Up here, you know, the customer may say, okay, you know, I want a higher slope. You go 3rd order, 4th order. Well, you go from 4, 8, 12, and 16 elements. And every time you do this, it slows the speaker down because it takes time to physically charge these items. And it's also, there's a phase change. And so if you put an impulse response through, you'll get ringing. And as you go in the no free lunch world, as you go left to right, the ringing gets worse. By the way, this one, the phase change is it's just 4th order. So it goes 90, 90, 90, 90. It's delayed and it's back in phase. So you don't have to change the phase on that one. But once again, this is how multi-drivers work, but there's no free lunch. A full range loudspeaker can be really realistic. There's a whole group of people that do them out there, myself included, because one of the things I try to preach is that we don't live in a frequency domain, we live in a time domain. What's happening in our brains and what's going on is all in the time domain. It's not the frequency domain. So getting things right in the time domain is the secret, which I've had some success with. So the other thing we have is we have a point source and we can have a line source. So on the left we have a point source, and this is just a single loudspeaker, and I've built ones like this, except used some drivers for a customer that's here. And one of the things I wanted to point out is I don't even know whose loudspeaker this is. I pulled it off the internet. But if you notice, I can take one look here and go, oh, it's a backloaded horn. So sure enough, there's the mount throat, and you can see that the mount is getting bigger as it goes down. And just like a compression driver, the back of this goes into a compression volume before it expands back out. However, on right, this is a loudspeaker I built. And this has 36 tweeters and 24 mids and 2 subs. Now, one of the things I want to point out about those subs, those are open baffle subs. But I've bent things around in such a way that it's a tortured path that's a little bit longer, and they work absolutely awesome impulse. Now, if you're close, if you're standing right next to this, it's multiple drivers and it screws you up. But at some point when you move farther away, you just think it's a solid line. It's a line driver. And that's because these are size, they're only 70 millimeters, and these are 19, these are non-standard industry. I'm kind of breaking the code a little bit. You get really good off-axis response, and the brain thinks this is a line source. Well, for a point source, when you move away from 2 meters or 4 to 8 to 16, it drops off 6 dB when you double the distance. A line source, it only drops off 3 dB when you double the distance. And this was an application for a the guy wanted to go into manufacturing it, but it's for a wine venue in Oregon. And so he wanted the complete audience to have the exact same experience. So as you move away from it, as you move away, it's only dropping off 3 dB. It's a little weird when you listen to it. The other thing is, because these drivers are so small, their off-axis response is good. The wine tasting venue was wider than it was deep. It was like 35 feet wide and I think 25 feet deep. So finally we get to a couple guys, Rice and Kellogg, and they patented the loudspeaker and basically submitted a patent in 1925. It was granted in 1929, but the point I'm trying to make is this is a technology that's 100 years old. And so a lot of people come up and tell you, oh, this is some revolutionary thing. We always giggle because like, well, it's evolutionary, but it's not revolutionary. And one of the things I want to point out in this is in 1925, this is an electromagnet. So if you guys ever get a hold of any old, really old radios that have an electric magnet on it, electromagnet, and it's a tube, fantastic. It's worth some bucks, especially if you store it. But this can have lethal voltages. This can kill you. So in 1940s, we were in war, and all of a sudden we're like, well, you can't put this big electromagnet on a loudspeaker on a B-17 and fly it. It's just too much, or in a Jeep or what have you. So they came up with permanent magnets. So in the 1940s was when permanent magnets came along, and the first one was Alnico, which is aluminum, nickel, cobalt. And so that's when things really exploded, because now we have permanent magnets, and that was one of the big steps. This was the first big step. The next big one was electromagnets. So now we're going to look at a voice coil, because that's pretty much what we're going to concentrate on. This is it right here. It's probably the most simple thing you ever saw in a sense. You got a mass and a spring. The mass is part of the surround, the cone, the weight of this, dust cap, the weight of the former, which can be heavy or light. You can make it paper, you can make it aluminum, all kinds of things, and then the weight of the voice coil. So you can make this former light, but then what's the no free lunch? It doesn't transfer heat, and that's one of your big problems. So in this formula, the resonant frequency of this loudspeaker is the stiffness over the mass. So the mass are all the things I've talked about. The spring right here is actually the spider. The spider is actually the spring in a loudspeaker. And it's a very antiquated device. That's one of my pipe dreams, is to get one of the springs, because the tolerance on these are like plus or minus 20%. And if you're a high-end loudspeaker manufacturer, you'll pay extra money to get plus or minus 10%. And when you pay that extra money for 10%, what they do is they pull it off the line, they test it, garbage, good, 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 garbage, garbage. That's how they separate the good ones from the bad ones. And also they're made in basically China and dirt floors, and it's really kind of tough. But what you have is you got an electronic circuit. You got a circuit that has to have a closed loop. Well, this is a magnetic circuit, and what happens is it goes through the top plate, through the magnet, around, up, and through, and that's your circuit. So over here, you've got obviously the surround, the cone. There's your spring. There's your former with your voice, and then notice the asymmetric vent that I talked about earlier. This edge right here is not the same as this edge, and that's so it pumps the air out to cool it. I think that's all it's going to go. There's the magnet. So here the path is this circle right here. Oh, one other comment. I come from mechanical world, right? Remember we talked about electroacoustics, it's double E mechanics, physics majors. So it's resonant frequency, which is one of the most key metrics, is the stiffness over mass. That's because I'm a mechanical guy. A lot of the people are double E's. So this stiffness right here is actually compliance. So it's a reciprocal. So you'll see CMS, which is compliance, but they're both the same things, but MEs versus double E's, what can I tell you? So the next big step was by these two gentlemen, the Thiele, who's Australian, and Richard Small, an American who went and studied under Thiele in Austria. And what he did was, you gotta remember this is 1960, so we're talking, 60 years ago. They just did a mechanical analogous circuit where they took mechanical items and put them in electric format and solved it. And what happened, the reason this is so important is these two guys basically, in the old days, you made a loudspeaker and you go, well, we put it in a box this big and it worked great. We put it in a box this big and it didn't work worth a damn. Why? I don't know, let's try another box. And so these guys had what's called QTS or Thiele-Small parameters, and they were able to put a metric on loudspeakers to show how they interact with the box and the volume of the air in the box and whether the port tube and things like that. And so he made advancements in the early 60s. He made the advancements in the early 70s. Richard Small is right across the river, so to speak, in Bloomington, Indiana, where there's just a plethora of high technology guys in the electroacoustics industry because Harman Automotive was there. So he's in Bloomington. As part of Alti, I awarded him a Brilliant Lifetime Achievement Award in 2015. Super nice guy, just an amazing character, but this is the next big jump in technology. And what it did was, we could now, and I'll get to it in a bit, but if you see up here, well, let's look here. I don't know if this is very legible, but here's QTS, which is kind of the total system damping. And the total system damping is comprised of electrical damping, QES, and QMS, which is mechanical damping. And they're in parallel, so it's kind of like 1 over QTS is 1 over QMS plus 1 over, they're parallel circuits. So what happens is this and this combine in a parallel way to give you QTS. And that combined with the VAS, which is the equivalent spring, the speaker has a spring, the equivalent air mass that has the same spring in a box is VAS. And we can combine these a little bit later, where they all of a sudden you see how they work in a box and you can predict pretty accurately. So up here we got resonant frequency, QMS. This is the manufacturer sheet. This is my test. And so you can see QTS. Over here you got obviously the moving mass. Remember I said the spring rate? Well, that's actually compliance. So instead of force per distance, it's the other way around. You got a sensitivity. Sensitivity is what happens when you put 2.83 volts in. And so, because amplifiers are voltage sources, and so your sensitivity will be different. They don't have the efficiency here, but the sensitivity will actually be different in your efficiency. This is how far the cone can go. And then you got to remember that that coil, the voice coil, is actually an inductor. Inductors are bad things when it comes, but you gotta have to have it. So this particular one I've chosen is because it had a low inductance, and that's really good. It means it has fast impulse response, means because it's acting like a 6 dB filter, right? It's cutting off the highs. Well, we don't want it to do that. So a lot of times this voice coil inductance, that could be 1.5, 3.5, 4. I mean, it can be really bad. The other thing I wanted to point out is here's the impedance curve, which when you do the test, you can extrapolate all this off the impedance curve. And so there's a nice pretty impedance curve, and here's what I measured. See this little blip right there? You can hear that. You can hear it. I can look at an impedance curve and tell you kind of what's going on just by sight. But you can hear. But this particular speaker, you would put a low-pass filter on it, so you may cut this one off at 100. So this problem out at 1 kilohertz, 1.5 kilohertz, no one cares, because you're cutting it off before it gets there. So I'm going to do a couple of things.
What does that sound like?
The
Blip.
distortion. Yeah. So it could be a couple things. I think, by the way, one of the ways you can cheat is you can take a frequency response measure and smooth it. And depending on how much you smooth, I've seen some pretty devious smoothing in my day. But this one is not smooth a lot, but I'm guessing that this right here, this little blip, kind of a breakup, and it'll show up as like either a rise or a suck out, or it could be distortion, could be a number of different things.
Pop.
No, no. No, this is, it wouldn't sound like a pop. This is, oops, oh, no, sorry. This is a little bit of a problem, but remember that these specs differ so much from this measurement that it's hard to go back and forth. But I do want to point out that the frequency response isn't flat, it has all these things. Well, if you look up here, on axis it gets real loud, but off axis it starts getting real quiet at 30 and 60 degrees. That's because the cone is not moving as a rigid piston. Part of the cone is doing this. It could be the surround is doing something weird. A lot of times that dust cap is really bad. As the sound goes, you know, it's operating as a piston, but the sound will travel out like this. When it gets out to the edge, it goes into this surround, and most of the time it gets absorbed because that's a damper. The point I'm trying to make is when the sound comes here and starts propagating up that cone, what happens to it? Well, there's sound propagating up this side, and they meet at the top. Now you got problems, because that is distortion. It's so bad, a lot of times people, you'll see loudspeakers, they just cut that out. But there's no free lunch, because this adds a lot of strength to this voice coil to keep it round. And you can get voice coil breakup too, although it's up around 15 kilohertz. Oh, there's how, that, by the way, that kind of shows, that shows an exaggerated, this is a laser that has measured all these, and it kind of shows you that kind of thing goes on. So this is all well and good, they're like, okay, Mark, that doesn't help me build a loudspeaker, so why don't you help me build a loudspeaker? So this is our first pass, and what we have is we have a sealed box, and the sealed box is 10 liters, I believe. Yeah, 10 liters, and it's QT, the box has a QTC, which is 0.707, it's maximally flat. And so the frequency response is good about 65, it's down 3 dB or half power point, F3 is about 65. And you're like, oh, you know, Mark, that's okay, but can't you do better? So, obviously I had these generated before I got here. But, so I'm like, okay, how about we put it in a vendor box if you want more bass? And so we put it in a vendor box, which is, I think it's 28 liters. Yeah, 28 liters, and it has a port, has a 60 millimeter diameter port. That port's about 330 millimeters long, so it's really long. But look how much more bass we got. I mean, it's like, it's an incredible amount more bass. And you're like, okay, you know, we're heading in the right direction, man. I want more bass. I want killer bass. So I'm like, okay, you know, if you want killer bass, there's your killer bass. Now the F3 is going to be about the same, but I've extended it way, way down. Now we're getting just tons of bass. And you're like, well, that's perfect, you know. But if you remember, in this industry, no free lunches. So now we're going to, now I've given you something, now you're going to see what I'm going to take from you. So the first thing I'm going to take is a box that's 10 liters, which is about 3/10 of a cubic foot, give or take. And then 28 liters, that's a cubic foot. 56 liters is 2 cubic feet, so we're just a hair over 2 cubic feet. So first thing I'm taking is, it's a bigger box. That's not even counting the port, because the port doesn't count, the tube that's in there, that doesn't count as a volume. So now the box is getting even bigger. So that's the first thing I'm taking from it. So what's the next thing I'm taking from it? Well, in the red one, which is the sealed box, its displacement the cone starts moving further and further, right? As you apply more power to it. But at some point, it can't move any further because it's a 10-liter box. It only has a motor strength to compress the air in a box, and it's given up the ghost, it's done. In this particular case, we've run out of X max at about 9, but really 10 millimeters is acceptable, going over because it has mechanical limits. But then we look at the vented box, which is the orange one, and we're like, oh man, we run out of X max at 60, 70 hertz, and then it comes back where it's in the motor's range, in this range right here. And then if you look at the extended one that I put in a real big box, man, it runs out of X max at, what is that, 60 or 70, and it runs out for the remainder. There's a little bit here where it's still in range. So that's what I'm taking from it. And what's going on is, in a vented loudspeaker, ported, bass reflex, whatever you want to call it, they have a tuning frequency. And the tuning frequency on this one is 20 something, what is it here? The tuning frequency on this one's about 30. Tuning frequency on this one is about 22, 23, somewhere around there. So what happens is, at this frequency, the sound coming out of the loudspeaker, none of it's coming out of the cone. All the bass notes are coming out of the port. But below that frequency, below the tuning frequency, which is here and here for ported speakers, there's no acoustic load on the cone. So if you go any lower than that, there's nothing to stop the cone. It thinks it's out in the middle of outer space, and it'll start flopping back and forth. And those of you guys who tried to play warped records back in the day, remember when you put the needle on the record and the record was going like this? And you look down your speaker, and your speaker was going like this, well, that's because it was below the tuning frequency. It was trying to play notes that were probably 10 hertz, and there's just nothing stopping. That cone sees no load on it, and it'll just go and destroy itself. The other problem we have, velocity in the vent. On this one, it's normally okay. This one, it's too high. And what happens is you get a huffing noise. And I have seen commercial loudspeakers built by professional organizations, mass manufactured, with huffing noise. Inexcusable. The last thing I want to go take from you, remember I keep saying, oh man, I love my open baffle because it's fast and its impulse is awesome. Well, last thing I'm going to take from you is in the sealed box, which is second order, right, and back in the thing, it's pretty fast, so it delays me about 4 milliseconds or so. That means it's lagging behind all the other signals by 4 milliseconds. The orange one, now we're lagging, 14 milliseconds. And the extended bass one was like 24 milliseconds. And so it's 24 milliseconds behind the tweeter and behind the mid-range. But you guys are smart, so you go, you know what? I'm just going to move the subwoofer closer to me, and I'll have the mid-range and tweeter back here. And that works. But from what I've taught you tonight, how far do you have to move the subwoofer to get it time aligned with the mid-range and the tweeter? It's 24 milliseconds. It's about 1 foot per millisecond. That means your subwoofer is 24 feet that away, and your mid-range is here, and of course, you're listening from the kitchen. Yeah?
How many milliseconds does your ear notice?
That is a source of contention. There's a lot that says it's about 5 to 8 milliseconds. However, I disagree with that. And I'll tell you, there's two things going on. First off, the brain sends, don't quote me because I can't remember this, but I think the brain sends 10 times the signals to the ear as it gets from the ear, and they don't know why. The second thing is, there's rock and roll musicians who are absolutely legally deaf and can tell a good loudspeaker from a bad one. And my question is why? And I don't have any proof, but I subjectively, I kind of speculate that's because musicians are incredibly time oriented. And remember I kept saying, oh, we live in the time domain, we don't live in the frequency domain. And that's why. They may not be able to hear the highs and the lows, but I tell you what, they can hear time problems. And I helped a Hungarian company launch a speaker, and it was an incredibly fast speaker. I mean, the impulse response on the tweeter was so good it could play to 50 kilohertz flat. It was an Omni. And so as I had people come in, I would and listen, audition to it, I'd be like, okay, why does this guy like it? Why? And the people that went absolutely berserk crazy were the musicians. And so I realized it kind of backed up my theory that it's time domain that is what's so critical. That we can live with frequency problems and linearity, but it has to be time.
I'm curious, you know, if you've ever gone to an outdoor event like an air show or a drag race or whatever, they got speakers on poles.
Right.
And you know,
Your brain loves that.
oh, it drives you nuts. What's the answer to that?
More speakers, closer, lower level. You also can do some other things. I'm working on a speaker right now with a team. Actually, most of the team is actually in Cincinnati, believe it or not. And we can steer a loudspeaker. So that's the other thing. You can steer a loudspeaker. You know, you may have a display in Kroger's or something where, you know, you got a bunch of these loudspeakers, and this one's saying, oh, you know, buy our carrots, and you take one step this way, you can't hear the buy our carrots, but you hear buy our popcorn or whatever, you know, and you can actually steer the signal.
That's the sphere. If anybody's been out there, do the display where they show you where you stand in 4 columns about the width of this room, and they turn the system on in front of you, and you walk between the lines, and you hear different languages speaking to you.
Yep.
And I'm the distance from here to that wall, and you can step a line, and it's in French.
Yep.
It's targeted. It's unbelievable.
Yeah, we're working on that right now, but we got a couple tricks up our sleeves we're trying to work on.
So the sensing of the time may not be in the ears, it may actually be in the body,
Well, no, what happens is your ears are the transducer and sending an electrical signal to the brain, and the brain senses that that the timing's not right.
But if you're deaf, how does it do that?
Oh, when you're deaf, when you go deaf, what happens is you start losing high frequency. So you can still hear, your sensitivity of the ear may not be quite as good, but really when you're deaf, you're losing high frequency. Well, what's legally deaf? Well, you can't hear S and T and all the ones, because really our language is not vowels. It's a bunch of consonants that are kind of together and they're kind of attached with vowels. But your brain is hearing the consonants. And so if you lose a high frequency, you can't hear S and stuff like that, then well, you're legally deaf.
So, yeah, so it's not stone deaf.
No. I'm sorry, I didn't mean to imply that. One of the biggest things, I'll take another second before I do the next one. One of the things that you see is that you got this woofer up here, right? And when you play a musical note, all music has a fundamental and a harmonics. So what happens is, let's say the fundamental is 100 hertz. Well, there's very important harmonics that you need to hear at 200, 300, 400, 500, on down the road. Well, if you have a 3-way system and you play that 100 hertz fundamental, what happens? Well, the woofer is going to play the 100 and the 200, let's say. The mid-range is going to play the 3, 4, 5, 6, 8, up to 1,000 or what have you, 2,000. And the tweeter is going to be playing them on up. Okay, so let's look at how things happen in the time domain. You send that signal to the 3-way loudspeaker, and the tweeter and the mid-range go bang, they play it, and then a little bit later, all of a sudden your woofer comes along and goes boom. And the brain's going, what the hell's going on here? And you don't go, oh, well, the harmonics. You just go, this sounds horrible. I don't know what's going on. This sounds like crap. There's things going on that are on the subconscious level that are absolutely phenomenal. To this day, we don't know why the brain is sending more information to the ears from the ear. I hope they figure it out one of these days. So what we have here is, this is a software my company built, and what you have here is a cutaway of a motor. So I've cut we're looking at the loudspeakers like this, and I've cut it like this, but just through the motor. And so we're looking at this half of the motor. So we have the pull piece, the bottom plate, top plate, the magnet. This is kind of represents the frame. There's your voice coil former, the red right there. That's your voice coil. And notice it doesn't go to 0. That's because it's a vented loudspeaker. There's a hole in the middle. There's a hole right there. Okay, this is what the magnetics look like for this speaker right here. And then I wanted to go through a number of things. In the 90s, Klippel and a bunch of other guys, Klippel out of Technical University of Dresden in Dresden, Germany, he started looking at loudspeaker nonlinearities. And this is the big next quantum leap. You know, you have Rice and Kellogg, and you got permanent magnet, and you got Thiele, and et cetera. But this is the next one. This is nonlinearities. And so, you know, our analogous circuit kind of assumes everything's linear. Linear with frequency, linear with magnitude. It's all linear. It works out great. That's not how it really works. So first off, this is BL. And this is the strength of the motor. Like BL is the number of turns times the B field. So the number of turns on the voice coil, the wire that goes around, it's the number of turns on the voice coil. So as you can tell right here, this displacement fore and aft, it's not linear at all. You start moving at all, and all of a sudden you start losing magnet strength. Not magnet strength, I take that back, motor strength. You're starting to lose motor strength, and that's if the motor's centered. Manufacturing, these things can have offsets. And you can, and that offset, I mean, we're talking 0.2 of a millimeter. Millimeter's 40 thousandths, so 0.2 of that. The other thing is, you know how I hate inductance, right? I've been kind of railing on inductance. Well, we look up here, we're like, oh man, the inductance, the voice coil inductance, it's all over the place. It starts and goes up like this. That's not good. Well, just to rain on your parade a little bit, just because I want to make your life just a little bit more miserable. This is a nonlinearity with cone displacement on the top right. Oh, it'll come back in a second. Oh, great. So now the inductance is not linear with stroke. It's not even linear with frequency. These are different frequencies. This is 63, oh wait a minute, 63, 250, 1K, and 4K. So the inductance isn't even linear with stroke or frequency. Now we got a mess on our hands. We can do some things to kind of fix it. How are we doing on time, by the way?
Is that, Mark, is that without motion?
No, this is the motion. The
That's-
motion right here, here's rest.
Yeah, okay.
And then here's 5 millimeters going backwards and forward, positive 5, negative 5. What happens is this voice coil right here starts moving out of the gap.
Okay.
So I'm trying to show that things aren't linear at all.
But neither's your ear, right? You're logarithmic with your ear, right? Your audio?
You're not logarithmic, you have different sensitivity. Well, yours.
Because you got logarithmic taper on a lot.
Yeah, it's all logarithmic, but if you look in log, your ear's not linear either. It has real high sensitivity, 2K, and then it kind of has a suck out, and then a 4K, and then it kind of drops off. But I can't design for the ear.
Oh, you don't try to design for the ear?
No. What I try to design where the transfer function is 1. Something comes into the speaker is the exact same thing that comes out of the speaker.
So you're wanting ideally linear?
Yeah, oh yeah, yeah. And a lot of people in a system, a lot of people, I'll try to share something with you, and this is just my opinion. The industry, I believe that we're supposed to be magicians, and we're supposed to do illusions of auditory senses. And we failed at it, and so the industry's kind of moved off in a certain direction, and that direction is what people like, not necessarily what's accurate. I built like highly accurate loudspeakers, and some people don't like it. But you'll see people that like horns, and that's what they like, electrostats, cones, etc. They all like different things. And so I think the industry's gone the wrong way, but I can't change the entire industry. I don't know, that's just me rambling on, but I find that we're going the wrong way. There'll be like problems with loudspeakers, and so guys, you love tube amps. And I've used tube amps, by the way. Yeah.
The microphone is a variable in this too.
Well, there's a thing called the circle of confusion. And this is where the industry's gone bonkers, because you got recording engineers over here, and you got musicians over here, and you got design engineers for loudspeakers over here. And of course, they don't talk to each other. And the other guys are wrong, by the way. I don't care what group you're in, the other guys are wrong. So the recording engineer hears a live event. Well, the live event has 0% distortion. That's it. You're listening to the live event. But the recording engineer, he kind of likes to do this, and he turns this little knob, that little knob. Now you're all kinds of screwed up. You know, placement of the microphones. There's a whole mess of problems going on. And then the musician comes in, and he's like, "What's he say? Louder, man!" So what do? We compress the signal. So now the signals that's going like this, we compress it down to where it's going like this. So you can play it louder because there's no transients. Because music's like this. That's music. It's a whole bunch. All music is a bunch of transients. Well, you can't play. You have to have a really good system to play transients. Well, if I squeeze the signal down to like this, where it's like this, I can play really loud because there's no transients. And so that's the other problem. So it's called the circle of confusion, and it just, you know, you record it, then you have the loudspeakers in the studio, recording studio, that's his personal taste, and then that goes out to the record, and it goes on and on. And we're in trouble now. I mean, what can I say? But the whole, I remember what I was going to say. The whole point is us being a musician and going my industry going the wrong way is that there is hope, because there's somebody out there that understands that we're supposed to be musicians. It's the movie people. Because the movie people will do stuff where you're watching the TV and you hear the guy walk behind you. That's what we're supposed to be doing. We're supposed to be faking you out. And so I'm hoping that I doubt it will happen, but I'm hoping that mentality bleeds over into the music industry. That's basically all I have. I can do one more modification, but only if you're interested. It has to modify some things, but only if you're interested. Yeah.
Can I ask a question now?
Sure.
The Bose speakers that are flat, but have a lot of, they have a pretty good sound quality. Are they able to get that quality by upping the power on the source, from the source? Or how
I don't know. I know, by the way, Omar Bose is like, along with Klippel and Klaus and some other guys, he's one of the big heroes in the industry. They do a lot of, Bose is really an advanced company, but they do a lot of, I don't want to call it trickery. They do things to get good sound out of relatively modest systems, and a lot of it has to do with DSP. The next big advancement going on right now, which oops. Let me show you something here real quick, if you don't mind. Uh-oh. I've lost. This speaker right here, this is my design, and every one of those speakers has its own amplifier. And the reason we do that is there's a couple reasons. Now that we have the digital domain, we can do a lot of things in the digital domain before we turn the signal into analog voltage and send it out. For this particular speaker, I had a microphone out here, and I measured the time delay of every driver. There's 24 mids, 36 tweeters, and 2 subs. I measured the time delay, and then I integrated that time delay into the system. So my system is telling the mids and the tweeters, hold on a long time until these 2 subs catch up. But instead of you, if I send an impulse to it, instead of seeing 3 impulses, one for the mid and one for the tweeter, I've arranged them to where they all hit at the same time. And when you do that, not only do you get right-left imaging, which is, if you do a good job, is fairly easy, you get fore-aft imaging. So instead of saying, well, the drummer's here, I'm like, oh no, the drummer's in back, and the singer's in front here. And this thing's a quantum leap, and it plays loud.
And that's at a certain distance from the speaker?
Any distance from the speaker. Yeah, what happens is this speaker also has a curve, and that's lifted from the sonar imagery, and there's a bunch of stuff going on with that curve there. And so there's a wave coming off that front, even though it's curved, there's a wave coming off that front, which is kind of a flat wave going out. And it's off axis, it's every bit as good as on axis.
And what was the application for that?
That was a guy who wanted to go in manufacturing, so we designed it. But he was selling them in a wine tasting venue. And the wine tasting venue was real wide. The off-axis response of any woofer or any diaphragm is a function of its diameter. So if you're real small, you can go way off-axis. But if you're real big, you start beaming. So this big 21-inch woofer here, as you start going up in frequency, it starts going boo, and as you go real high in frequency, not very high now, maybe 1,000 hertz, it's beaming real bad. Where these tweeters are 19 millimeters, they're not beaming at all up to, I think they're 3 dB down or something off axis at 13 kilohertz or something insane. That's really good. I mean, a high quality tweeter off axis is good to maybe 9,000. These are good to 13. Yeah.
Say you've got a venue, an auditorium that you want to outfit with speakers.
Yep.
How do you determine the number of speakers in the auditorium? I mean, I know we're talking about tweeters and woofers and mid-range, but in terms of multiple speakers, okay, that are actually broadcasting the same thing.
Well, I think, okay, what's the source material?
Because on your diagram, you had 2 speakers, sweet spot,
Yeah.
okay, 3 speakers, 4 speakers.
Well, yeah. The industry will, even in a PA system, which is Pro Sound, as opposed to home audio, the Pro Sound will also try to do 2 speakers. If you go to most places, they have 2 speakers, but the stereo imaging, forget it. It doesn't happen. My theory, which no one ever does, by the way, is that they would all be centrally located and splayed out like this, so you would have one single source. The number of them depends on what kind of SPL you want. I mean, do you want it super loud, or is it a guy talking, or, I mean, you know, this works great for one guy talking, you know, not loud or not playing music. And so it depends on, you start with the requirements, and I can't answer your question without the requirements. Yeah,
The venues I see that need help now are all the indoor pickleball places. These people don't know what they're doing when they do a flat floor building, block walls, and I went into one owner and I said, just hang a bunch of drapes in this place. It's really cheap. Just take the reflection off the walls.
yeah, they don't. One of the problems is that acoustical materials, I can take fiberglass and charge you $1. If I take that same fiberglass, make it acoustic, it's exact same fiberglass, now it's $5. And so the second you put acoustic in front of it, the price goes way up, even though it's the exact same material. So people like that, they kind of get hurt, but one of the things that does remind me is that if you have a sweet spot in a stereo at home and you know, if you put no absorption on the sidewall, the image will be real wide. If you put absorption on the first bounce, the image gets a little bit narrow. I'm a narrow guy, but I'm the minority. Well, the whole point I'm trying to make is if you're sitting here, you can have somebody hold a sleeping bag and just go like this and go, okay, that sounds great right there. And you're like, okay, that's where the absorber goes. And then you go buy an absorber. One of the reasons I brought up about the sweet sound in the room is because some of the biggest improvements are the cheapest ones, and that's your room. And moving the speakers. I've seen 6- and 7-figure systems. There are 7-figure systems out there. I've seen a lot of 6-figure systems where, they spend over $100,000 and it sounds like this because the room is crap and they won't even move the loudspeakers. They'll spend $5,000 on a new cable, but they won't move that loudspeaker around to get the best sound out of it. And it's criminal.
Have we got any other questions for Mark? Well, let's show him our appreciation.
If we have some geeks here, I can do some loudspeaker testing, if anyone's interested.
Thank you.
Thank you.